but I can see the screen, so life is good.
All right. I'm going to stand to make that. Good morning, and welcome to the SciTech 360 Forum on advanced manufacturing and its impact on the design process of the future. My name is Graham Kennedy, and I'm an assistant professor at Georgia Tech, and I will be the moderator for this panel. And the purpose of this panel is to discuss advanced manufacturing and how it will impact the design process. And to do this, we've got a number of both leaders from industry and academia who are going to be on the panel. We have Steve Betza, who is Corporate Director for Advanced Manufacturing and Development at Lockheed Martin. We have Andy Beisos, who is Director in the Manufacturing Technology domain at Boeing and works in the Enterprise Technology Group in the Office of the CTO. We have David Rosen, who is the Morris J. Bryan Jr. Professor and Associate Chair for Administration in the School of Mechanical Engineering at Georgia Tech. We have Mark Shaw, who is Additive Engineering Leader at GE Aviation. And we have Art Weiss, who is Executive Director for Defense Advanced Programs at Aerojet Rocketdyne. So the format of the panel will be that the panel will begin with some prepared remarks from each panelist. And then next, I'm going to ask a series of prepared questions that the panelists know in advance. And then we will take some questions from the floor. So the starter question is, how can design methods and practice evolve to maximize the benefits? Pardon me. We're going to start with prepared remarks.
That'd be good.
Okay. This is to you, Steve.
Well, ladies and gentlemen, good morning. Thank you for taking the time to join us here today, and thanks especially to Graham for hosting us and being the moderator, and it's great to be with you all. I'm Steve Betza from Lockheed Martin. I was going to just do a very brief opening of what is advanced manufacturing in Lockheed Martin as to set the context for the design method discussion to follow. Possibly the greatest challenge that large manufacturing enterprises face today is successfully transitioning new technologies and processes from the lab to production. Those of us that are familiar with MRLs or TRLs sometimes call this the valley of death, of how do you get from MRL 4, which is functioning in the laboratory, to the production environment or production ready, which is MRL or TRL 7. At Lockheed Martin, we're addressing this challenge with a multi-year initiative. We call this Accelerating Manufacturing Innovation, and it's focused on 4 strategic manufacturing threads. So we take a broad view of what advanced manufacturing is, first of which is additive manufacturing or industrial 3D printing, advanced materials, including nano-modified materials, polymers and metals and composites, what we call the digital tapestry for manufacturing, or the seamless digital environment that connects engineering to the factory floor to our suppliers, and lastly, next generation electronics. The big focus there is how can we dramatically reduce size, weight, power, and cost, SWaP C, out of the electronic systems within our platform. So those are the 4 research threads that we have. And then within each thread, we really have a 5-part strategy. The first is called Connecting the Community. We have nearly 60,000 scientists and engineers within Lockheed Martin. So getting the dialogue going and the innovation flow across them is job 1. The second is what I would call high-value, pre-competitive or public domain research. And we are Tier 1 members at each of the presidential NNMI manufacturing institutes that are being stood up by the DoD, Department of Energy, today, and that a number of them are still in the competing phase. We see those institutes as a great opportunity to do collaborative work with our industry partners and with academia. Third aspect that we do within each thread is proprietary research across our business areas. The fourth is workforce development. And the fifth is really partnering with our customers so that we can advocate for advanced manufacturing and for manufacturing in the United States at the national level. So I will just conclude the opening by saying we are observing that this renaissance in manufacturing is having a positive impact on design methods. It's exposing us to a realm of possibilities that's a backfeed to the front-end design process, and we look forward to the discussion on the panel today.
Thanks. My name is Andy Bikos. I'm from Boeing. I'm going to sort of frame the problem in a larger context. One of the major challenges within aerospace today is really the enormous increase in development costs over the last few decades. If you look at aerospace systems versus automobiles or electronic systems, the costs in aerospace system development time is just gone significantly, multiple times higher over the last few decades, whereas in the automobile industry, as complexity of a car has increased, or in electronics, the costs have been flat or even going down in real dollars. So we have a big challenge in that, and part of the two major elements of that is the non-recurring and the recurring costs. And so, the majority of the life cycle costs in a system is locked in by decisions that are made early in the design process. And what ends up happening is, because of that, when you find problems, you have this design, build, test, redesign. And the more problems there are, the higher the cost goes. So as the complexity of the systems goes up and we introduce new technologies and they're not necessarily at the right MRL or TRL levels, that's a lot of risk that then comes and impacts us later in the program, which leads to significant costs. So I think one of the things that we have to think about is, how do we improve this design, build, test, redesign process? And when we look at advanced manufacturing technologies, that we look at them to help us increase performance, but also reduce the recurring cost. There is always a lot of hype regarding the benefits, and we tend to downplay the cost that might be associated with that. And whether that's implementing things like advanced composites, automation, robotics, 3D printing, new materials, I think that the trend is the same. If you take composites as an example, I mean, we in my company have put a lot of effort in composites on the military side. We made a big push on the commercial side with the 787, and if you look at what it costs to do a structural certification, as an example, the number of tests that are needed in the 1980s to structurally qualify a system, something on the order of 5,000 tests, whereas in the 2000s, it was well over 100,000. So, when you introduce new technologies, you've got to think about those costs and how you mitigate them. And I believe that those trends are going to be the same for things like additive manufacturing as well. So I believe that one way to break this increasing cost curve is to more adequately design the manufacturing process that we're going to use in our factories, and then things like 3D printing, automation, robotics, and other advanced technologies that come along, we'll be able to implement them with a little bit more foresight in what the impacts might be. Many times many times these new technologies are taken and you build the part that's already designed with the new process. And the design is not taking advantage of the full benefits of that process. And we've done this many times, and again, you can use 3D printing as an example, where you build the part, but it's a nice demonstration piece, but you wouldn't necessarily want to fly it. And I think this is the hype that I see going around and talking to folks, is that they think that you get the part out of the machine and you can bolt it on and you can fly away with it. And it's that they've bought into the hype. There's a thing called the Gartner hype curve, and 3D printing has been at the top of that for the last few years. So I think there is a significant amount of work that's needed to fly additively manufactured parts. We're flying currently about 20,000 parts on our vehicles, both on the commercial and the defense side, predominantly polymer-based, but we're moving into metallic-based on the additive side. But because additive and the other advanced technologies in manufacturing that we're looking at offer so much potential, I think that we have to understand all the variables in the process. We have to design the process for the specific application, and then design our vehicles to take advantage of those manufacturing processes. And the thing is additive's not the end-all and be-all. Automation and robotics isn't. Composites isn't. But the combination for specific applications and the smart design of the whole system to use all the various manufacturing tool set that we'll have at our disposal is the key. And that really is a big systems level design problem. So I believe that what it's going to require us to do is incorporate this into the early phases of design and optimization process. So things like including manufacturing and the life cycle costs in the MDAO processes that traditionally have just been sort of aero and structures has to now include those life cycle costs to really be able to give us any chance of changing the paradigm and breaking the cost curve. Thanks.
Good morning, everyone. I'm Dave Rosen in Mechanical Engineering at Georgia Tech. I thought I'd take a different approach here a little bit. Graham asked me to talk about design for additive manufacturing, and I thought the best way to do that was through a series of examples, and I'd like to use slides to convey those examples. So first of all, I had a great introduction here about additive manufacturing. To me, the idea of design for additive is all about taking advantage of the unique capabilities of additive manufacturing. And for the purposes of discussion, I'll highlight four. One is you can make just about any shape. Second of all is, at least in principle, you can put different materials where you want it. You can process the material differently to get different mechanical properties locally, again, at least in principle. Hierarchical complexity, features can have features, and finally functional complexity. With a lot of these kinds of processes, or we can think about hybrid processes and actually make functional devices right out of the machine. Many of you are probably familiar with the F-18 jet fighter example from Boeing and Northrop Grumman. This is just a really good example of taking advantage of some of the unique capabilities of additive to do part consolidation, simplification of the design, and also optimize the functionality. And so on each of these F-18s, at least the numbers I knew about a few years ago, was between 40 and 80 laser sintered nylon parts were on each of these aircraft. You can see some of them here, and Boeing reported 50% cost reduction, 67% cycle time reduction. I mean, these are really, really significant numbers. Looking at some of the more research things here, additive allows you to design and fabricate compliant mechanisms, morphing structures, things like that directly. We could even think about deployable or inflatable structures. Design your optimized design, fold it up, fabricate it, inflate it to deploy it. Some people are looking at hybrid technologies where you can make the structural part and then also direct write electronic components on top of it. Some very interesting possibilities there. The whole area of cellular structures, foams, lattices, honeycombs, things like that, additive can really revolutionize that area. Ever wonder why a woodpecker doesn't get a headache? Well, in part, it's the construction of their skull, the cellular construction of their skulls and beaks. cellular structures can be used to make very lightweight, strong, stiff, energy-absorbent structures, et cetera. Okay. At Georgia Tech, we've been developing a series of software tools that allow you to design and optimize lattice structure. This is one particular example of a handheld UAV fuselage that was designed using our software. And a couple years ago, we fabricated that in nylon laser sintering, flew it, and compared the flight characteristics to the production carbon fiber design. And the results were very good. Many of you, I'm sure all of you, are probably familiar with topology optimization. You can get some pretty complex-looking designs out of topology optimization. Additive potentially allows us to fabricate them directly. While you're doing topology optimization, one of the approaches is to compute a variation of density. Well, you could potentially map density values to lattice structure sizes, things like that. And so you could potentially design structures like this, fabricate them directly. Polymers, metals, doesn't really matter. So again, series of snapshots, but some of the design principles come back to, again, complex geometries, take advantage of it. We can consolidate parts, fabricate fewer parts, avoid an awful lot of assembly operations and assembly tooling, custom geometries, multifunctionality through a variety of mechanisms, no tooling, or you can fabricate the tools using additive, efficient use of materials, and finally, particularly if we can come up with lightweight structures, much smaller carbon footprints in terms of fabrication and life cycle usage. I'll just conclude with the concept that with the advances in computational materials design that a lot of my material science colleagues have been developing, we can now at least think about simultaneous design of parts, materials, and processes, and take advantage of the capabilities of additive to process the material differently in different locations to get different properties. With that, thanks for your attention, and I'll pass it along.
Hello, my name is Mark Shaw, GE Aviation. Extend my welcome from sunny and warm Cincinnati, Ohio. So my story in additive manufacturing started March 2011. March 2011, our vice president called me into his office and he said, "Mark, I'd like you to lead our fuel nozzle team." And at that time, at this point in my career, I frankly didn't have a lot of interest in leading a fuel nozzle team. At that point, we were sourcing out the design and manufacturing of our fuel nozzle. He explained to me that this was a pretty important project, and this project the most senior executives in our company knew about. And he said that we were thinking about using a technology called additive manufacturing. I accepted his proposal, being that he was a vice president, and he told me it was important. So I said yes. And so we basically started this team. It was myself, my boss, and we had selected what I'll describe as probably the brightest young engineer in the company. So if you think about a company like GE, I don't know how many engineers we had, let's say 5,000 engineers to pull from, and we selected the brightest young engineer in the company to be my lead engineer. So I started hiring at that time. He told me in that meeting that this thing felt like 50 people. I had at one point 30 direct reports. In the core of the team, I sometimes described as this one bright young engineer and 7 college graduates working with him. And as we started to design this fuel nozzle, we were using 3D printing additive manufacturing. And all our parts were being made by Morse Technology, which is located in Cincinnati, most of you know. And we were essentially what we were doing is we were making the fuel nozzle, and this is a lean burden fuel nozzle, so it's more than a tube and an orifice. It's actually a very complex subassembly with lots of parts in it. And we were essentially just replicating the subtractively manufactured part additively. So if those of you who do 3D printing and additive manufacturing, you've been down this road before, right? I heard you describing a very similar experience. We've all been down this road. And so, what I often say is, and I see this still see it every day, so this is the engineer who walks into the 3D printing shop and says, "Can you print me one of these?" Right? So that's basically what we were doing. And so it was June of 2011 that my lead engineer walked into my office and he said, "Mark, I think we're thinking about this completely wrong." I said, "Oh, what are you talking about?" He said, "I don't think we ought to be printing these parts individually. I think we ought to be printing them all as one." So you described, so you guys have all understood this. He said, "I think we ought to be combining these parts all." And I said, "That sounds awesome. Let's go do it." So it took us some time to rethink this whole idea of what a fuel nozzle of all these tiny little pieces looks like. So there's a design paradigm that had to change at that point as we had to think about what a subtractively manufactured part designed as 20 individual pieces, what would that look like if we printed it as one in a manufacturing process that grew from the bottom to the top. And it took us 3 more months to be able to not only conceive the design, but trial and error, because if you've been through this process, you grow it and it crashes, and you grow it and it crashes, and we finally were able to do it. And so 3 months later, we successfully grew our first one-piece fuel nozzle. And so that's really the story of how the GE LEAP fuel nozzle came into being. And so from that beginning was this belief that we now believe that this technology has an opportunity to really transform not only the way we manufacture parts, but the way we design parts. And the outcome of that was a part that was 25% cost reduction, 30% lighter, and most importantly, this component goes from a wide body to a narrow body, and those of you that understand that the wide body is a 3,000 cycle machine, a narrow body is a 20,000 cycle machine, needed to meet durability requirements that were about 5x of what its predecessor was. So what was the 20-piece component, which was a 3,000 cycle component, now had to meet a 5x durability requirement. So what additive manufacturing not only helped us meet a weight requirement, it actually helped us meet a durability requirement. And so the flexibility of combining all those pieces together and being able to change the geometry, all those things that you just heard described here, so cost, weight, now even being able to change durability, all of those requirements that in the past would have been frankly impossible to meet using traditional manufacturing processes, now unlocked. And I'll be honest, when we started on this journey, we didn't understand those things. And so where I sit today, I no longer lead the fuel nozzle team. I'm the additive leader for aviation, because through this process, we acquired Morse Technology because we understood the bringing together of the manufacturing and the engineering together. This is an opportunity, not for us, but for our entire industry, to really fundamentally change the way we think about the way we develop and manufacture our products. And I'll tell you, when I got this invitation to speak, I've spoken at a lot of these, I get lots of invitations to talk about the GE LEAP fuel nozzle. This is probably the only invitation that was specific to design. So I was really excited to come and talk about what is different about the way we design fuel nozzles. And I think we're only beginning to understand that this not only changes the way we manufacture the part, this fundamentally unlocks opportunities. And I think that's why you're all here. It changes, in the example of the fuel nozzle, it allowed us to do things that we otherwise could not have done if it were not for additive manufacturing. So more to come.
Thanks, Mark. I'm Art Weiss from Aerojet Rocketdyne, and as part of my role of running Defense Advanced programs, for a number of years now, we have been attacking the design side of this particular problem. As Andy talked about, the affordability part of the equation has now risen in priority. Dave and Mark have talked about design aspects in terms of integrating complex pieces into single pieces. But we have been on a journey for the last 20 years to try to understand how to shift the design paradigm in order to take advantage of whatever new manufacturing technologies might be coming forward. Additive, clearly a key item that we are pursuing, but in parallel, we are changing the way we look at design. And I've got a couple charts I just want to give you a feel for how it is that we're attacking this particular issue. So again, changes in manufacturing technology have allowed us to increase the integration of our designs, reduce the number of parts as we drive towards this affordability objective. It also allows us to change the way we think about the system, and that's where we're going. And we've coined a few terms in-house to allow our folks to get acclimated to this change in thinking. And that first term, in thinking, is actually a set of thought processes that we've put together over the last several years that help us take a look at design from a totally different perspective. We need to take a shift here from the traditional way of designing parts that then link together into a system and start talking about a system of interdependent parts. When you start looking at things that way, as Mark has pointed out, it opens up a whole new world of thinking in terms of possibilities with the design. And you start to recognize that we can indeed change this design, test, fail, fix paradigm that we're in, because once you can do that and execute designs and produce them first time through, obviously time and money are saved. So it's very key. So how are we doing this? We've coined a term, business as unusual, because we're focusing on how well parts play together. Not so much whether or not the individual part is good or bad. It's not about parts. It's about the way the system operates. And so we've changed our designers' perspective to thinking about the system as a whole as they are sitting down to design the pieces that are part of that system. And then how are those parts going to get made additive, then making a major difference in how we can do that. So we've put together a series of processes to do that. We call that mixed model management. And again, it's all a shift away from the traditional pass-fail type criteria. We're kind of driven by a quote from Russ Akoff. He was with the Wharton School, but he kind of led us down this path in terms of the fact that it's managing interactions. It's not about managing actions. And so a way to graphically portray that, normal system thinking, system engineering thinking is what we call the macro system. Basically, you tolerance parts, and as long as you're in the band, you're good, pass, fail. Problem is, we all know, and we've had examples where all of the good parts come together in the assembly and they don't fit and they don't work. And why is that? Because we didn't understand the fact that it's all about variation, and it isn't about whether it's pass, fail, it's about whether you're hitting the target or not, and what's the distribution of producing parts around the target. And so advanced manufacturing techniques are giving us the ability to narrow that band of variation around the targets that we're after. And it's the targets that the designer needs to be worried about in order to make the overall system work better. So for us, it's now about minding the gap, the interdependencies between the parts in the overall system, not just the individual part. We've even taken a look at some of the characteristics that we normally do things with in the macro system, and then taken a look at what we got to do if we start looking at things in the micro system. And we're all pretty conversant in how to do systems engineering at the macro level, but when you start taking a look at things at the micro level, it's a new paradigm. And it's been very difficult in the first few years to get our design teams to understand the fundamental differences here. But once they've tumbled to it, they've begun to produce some very interesting designs as we go forward. So our approach right now is to infuse this whole line of thinking throughout the design organization at Aerojet Rocketdyne. We're actively doing that today. It's all about minding the gap, and we've made considerable progress. The additive manufacturing activities have allowed us to even accelerate some things. Integrated designs that, as Mark has pointed out, that we never thought were possible before are now possible. And so this understanding of the microsystem is opening up brand new capabilities for us, and we see a great future in going down this particular path.
Thank you. So I think you've each touched on this in one way or another, but I think the overall question that we're trying to really address is how can design methods and practice evolve in light of this huge potential of both additive manufacturing and advanced manufacturing? So how can design evolve to maximize the potential benefit of these manufacturing technologies? Steve.
Well, within Lockheed Martin, we've been taking almost a 40-year view of where is design evolving to. And if you look back to the first 15 years of the 21st century, and so think of the state of the practice in the year 2000, and then let's telescope out to around 2040. There's 5 areas that we see where the design process is evolving to. I think all of them are very consistent with how to adapt and embrace new technology insertions that advanced manufacturing offers. I'll throw some ideas out, and then of course my colleagues here will expand on them. But we certainly see a design process of the future as being centered on model-based system development, the development of behavioral models that will characterize a system at the beginning of a design, and then increasingly synthesizing the hardware and software elements that come out that become part of the final product. We've been getting very good at that in the software domain over the last 1 to 2 decades. We're starting to see the ability to synthesize designs in digital logic, for instance, if you think of programmable logic. And then I think the next big frontier is actually beginning to synthesize mechanical structures and the interface to CAD systems as you model to them. So that's number 1. Number 2, there's an area of work that we're doing in called agile and collaborative engineering. Software community, again, has been a thought leader in what's been called agile practices of starting with your requirements set for a design and then going through a series of sprints or iterative cycles of a design to prove out. We believe that's also transferable to hardware profession. And we're starting to see, and if we take additive manufacturing as example, the ability to prototype very rapidly, the ability to have an object back in a designer's hand in a matter of hours or days, allows that set of sprints to occur and iterative design journeys. Also, a set of, let's call it next generation IPT methods, where we really focus on eliminating risk as early as possible in the requirements phase, and also prototyping to eliminate risk if there's new processes being inserted. So agile and collaborative is number 2. We see a great focus on test automation, and especially reusable test automation, because as systems get more and more complex, as we're all witnessing today, being able to have reusable, reconfigurable test suites that will shorten the cycle time and the cost of system tests, very important. I mentioned a digital environment as being very, very key. That's number 4 for us, is to have a seamless environment that conducts or connects engineering to manufacturing to the supply chain. And lastly, it was outstanding as we were talking about this across the row, I believe there's going to be a renaissance in design for simplicity, in that we've all, if you look at any one of the design for X activities that we've had over the years, whether it's design for producibility, reliability, maintainability, cost, design for simplicity properly done harvests all of those for you. You reduce size, weight, power, and cost. You have a more maintainable, more producible design. And I believe there'll be a renaissance in academia and in practice of new design thinking with simplicity. So that's some initial thoughts from us.
I agree with all of that. I think that the other thing that we need to think about, and I saw part of it on your slides was really looking at the design of the whole process, from the design of the manufacturing process, the design of the materials, design of the end product as one design activity. I think that is where one of the parameters that you're optimizing around is the life cycle cost, not just performance, and driving that into our tool sets and our processes is what's going to be needed to really provide high performing yet affordable systems that we can develop in a ever shorter and shorter time span that's required to remain competitive in the market in the future. So I think that is, and there's a plethora of technologies and activities and design methodologies that are needed to be able to pull that off. So I think there's lots of great challenges ahead for us to do that, and plenty of work for everyone in this room and beyond. So.
Yeah, design for simplicity, that's a great idea. I'd like to expand on that. One of the distinctions I like to make is between design for manufacturing and design for additive manufacturing. DFM is all about understanding the constraints of the manufacturing process and figuring out how to live with them. Design for additive, on the other hand, is all about exploring unexplored design spaces. It's coming up with new ideas, new design spaces, going where people haven't gone before because they never had the opportunity. And in order to do that, all you need to do is come in the morning and say, well, today is I'm going to be creative today. No, it's not that easy. This is really hard. In fact, we actually need new design tools, we need new design systems, and we need new ways of, new design methods, and really understand how people come into play here, how people can be very effective together. Because we're not going to be able to rely on individual creativity and innovation. It's really going to be a system and organizational achievement with a lot of the focuses that these guys have talked about.
Yeah, no, I like exactly what you said. So let me offer you two experiences that we had in the development of the LEAP fuel nozzle. The first of which was, and I'm a little OCD, so forgive me for if this sounds a little bit crazy. So I organized my team in a lean flow line. So, and if you understand combustion design, you understand how many disciplines that are required. So I had my combustion aero guy, I had my fluids CFD guy, I had my thermal design guy, I had my mechanical design guy. I'm probably forgetting someone. So you get the idea. So, and I had my CAD designer sitting in the middle. And I had mechanical analysis, the stress guy. And so they were all in sort of this circle around the room. And so it's sort of this idea that we would do in a single dimensional problem where you can send it off to the computer and it does this, what do you call it, when it optimizes on a single parameter and comes back. Well, it was too complex to let a computer do it, so I had to let a room full of people do it. But we had to optimize on all these parameters, and we also understood that this part had different manufacturing. And I like what you said, they're not so much constraints, but understanding the manufacturing process, that we're now growing this like a tree from the bottom to the top. So there's some things we want to keep in mind about how we want to design the part. And a lot of that relies on my lead design engineer and the CAD designer. And by the way, just a note about the CAD designer, you need rock star CAD designers. You saw some of the shapes that he had on his slide, right? It changes, in my mind, this changes the world of what you need in CAD design. The guy who designed, just as a data point, the guy who designed this fuel nozzle used to design body panels for one of the major automakers. So he knew no straight line, and it was perfect, right? So that's just a sidebar comment. So you can imagine what this thing looked like. So CFD, flow, thermal, mechanical, is this manufactured the right way? And around that circle we went for months after month until we got this thing particularly sculpted, meeting all those requirements, right? And the thing that we weren't so much focused on, can the cutter get in and out? Can we assemble it? Does it have the right draft angle? What we were looking at, does the fluid have a recirculation zone? Is the stress got uniform strain lines? Is it isothermal, right? What are all those? They're physics, right? We're designing to the physics of the problem. And I don't care if the wall thickness is uniform wall thickness, because the printer doesn't care, right? Right, so you know where I'm going with it. So the printer doesn't care about all those things that so I love the way you said the old manufacturing process, we were constrained by straight lines and circular holes, and when I drilled a hole, it had to be straight. I don't care about those things anymore. So that was the one, that's probably my one thing I'd want to offer around design, is really designing to the physics, but understanding the manufacturing process as you go. The second thing I'd like to offer in this, and I heard this one as well, is, and I'm a mechanical designer if you can't tell, I loved to design, build, test, and get the result before the CFD guy was done. It was just awesome for me. Because we could do it. And understand combustion CFD, the reacting flow CFD is really hard, right? If you have the right mesh density, and I mean, that's not easy stuff. But there was, you remember when we first got computers, maybe some of you are too young to remember this, and we used to say, there's gonna be a time when we just build these, we won't have to test anymore. Remember that day? We'll just build these models and we'll just analyze it, and we'll just certify the engine or certify. We've actually turned that on its head, because I can design, build, test empirically and get the result, and I tend to believe it, particularly in combustion science, before I can actually get some of my test results. Because, I mean, we're printing these things in days, and I'm not sending them off and getting them back in months anymore. So that's the other thing that's really, from a design standpoint, has really changed.
I would add only one other thing. All of what you all have said are all pieces of this puzzle to the answer to this question. I think the one additional thing we have to recognize is that there are so many pieces, if you will, in this process that we've got to move towards a new approach to managing the entire process. And so when you look at a product, not only just the life cycle, but it has a value stream. And it's changing the way we manage the programs to manage the value stream and all the intricacies that go into that value stream, not just the design, not just the manufacturing processes, not just the supply chain, all those pieces ultimately come together in that value stream. And so learning to manage the value stream with these kinds of nuances, the new way to look at the design, the new manufacturing tools, is probably going to be the biggest challenge, the ultimate integration. So value stream management is going to be coming to the forefront.
Well, I think both David and Mark touched on this, but this is sort of a dive into the actual design. To do a design, we need design parameterization. And often we're using CAD to do conventional design. Now with these advanced manufacturing techniques, do we need a different parameterization? Do we need to describe things in terms of the manufacturing process itself? So have a description of how the part or component is manufactured and use that as the design parameterization? So I'll open that up to you.
I'll jump in with that. And let me go back to the last slide that I presented. The simultaneous part material manufacturing process kind of idea works if you have a few things, and one is a new parameterization. And the second thing is you need some kind of multi-scale computational environment. because you have things happening at the micro scale, at the millimeter scale, at the macro scale, et cetera, right? And what enables all that is to have the materials, process structure, property relationships represented and modeled in a way that you can reason backwards and forwards there and use those relationships to really understand what's going on in the physics while you're manufacturing and how it's going to affect the properties and the microstructure, because you need that property, you need those properties and the property distributions in order to do any kind of meaningful analysis on these kind of parts. And so, one of my, are there any CAD vendors in the audience? One of the things I like to kind of pick on is parametric solid modeling is a great technology. It's revolutionized design and product development, but it's not going to be the fundamental design technology that carries us forward when we try to do this multi-scale, simultaneous, anything involving the materials in the manufacturing process.
So I'm going to say something that's not really true, but we say it anyway. We say if you can draw it, meaning draw it in CAD, you can print it. And in a sense, that's true, because we've done it. But in a sense, that's not true, because you don't always want to print it. So we can print any part, any shape, but it's really a factor of cost at the end of the day. So the way I'd probably answer that question is, the thing that has changed here is I do believe that physics leads design. And what we didn't really realize until additive manufacturing is how much manufacturing led design. And I think we were just blind to it, at least most of us who had been doing this for so many years, is if somebody challenged us and said, that part is designed by manufacturing, you'd say, oh, no, it's not. I engineered that part. Well, why does it have round, straight holes on it? Well, that's the shape of the drill. Why does that have a fillet radius? Because of stress. Well, why is it a radius? Why doesn't it why doesn't it look like a tree branch? Why doesn't it look like the inside of a bird bone? Well, that's crazy. Well, that's the way physics wants it to be. So there is the balance here is that when our design teams designed a physics, they still need to know that fundamental understanding of how the manufacturing process works. And so what we have done, and I'll be honest, we're still struggling with this, as all big corporations do, is we still think in terms of supply chain and design. But we're working really, really hard, particularly in these advanced manufacturing, is just to say, these really shouldn't be two separate functions. Really, they should be, my designer should be the person who also understands the manufacturing process just as well as the guy who runs the machine. And in the case of the fuel nozzle, I will tell you, the lead engineer thoroughly understood, as well as anyone else, how that process worked, and that's why we were so successful. Now, going forward, is that going to hold? We're trying. We're trying to make that model work. But I will say physics leads the design, but you all know it can't be with the exclusion of being completely blind to the manufacturing process, or cost will suffer.
I would add to that I think that the physics is also in the manufacturing process, and especially if anyone's ever worked with an additive manufacturing machine, I mean, and you can get inside and adjust the various parameters on the build rate, the power, there's a lot of tweaking that can be done. So you can, as I'm starting to think of the design, I'm thinking of designing the process for the part and the part for the process to get the objective that you're going after, or the parameters that you want to satisfy, and so because depending on the build rate and the power, I mean, you get different material properties, different anisotropies. I mean, so it opens up the design space immensely. But if you don't specify that, I mean, you don't know what you're going to get. So it's got to be part of the design. And then we've got to have tools that enable us to analyze that so that we can predict, what we're going to get, so that we can then optimize around that. Again, with the design being not just design of the part, but design of the process, and looking at that as one holistic system.
All right, so with new manufacturing processes, there's always the issue of certification and of ensuring safety, which is really essential. How can we use design to assist there, or what can we do to make sure that the sort of path to certification is as clear as possible?
I'll open with a thought. First of all, if we were to just stay with additive manufacturing for a second, there is a very large opportunity space to put additive to work in all of our companies that is not just safety critical parts. I think there's been great demonstration shown of the power of prototyping and how that's becoming almost a ubiquitous capability in all of our companies, partnering up with designers. We see great benefit in machine tool and assembly aids of being able to deploy additive in on an assembly line for fuselage development or the like, where fixturing that we would have done that would have taken weeks or months is now done in hours or days. That's a tremendous opportunity that's at very low risk and yet great business value. Then even when you think of delivered products, let's put those in two categories. One would be non-safety of flight critical, and the others would be safety of flight critical. So there's an opportunity to get additive into your production stream on those relatively bounded environmental cases where you can safely do it and do it a little more aggressively. And then you take great care when you've got flight surfaces or human safety involved in terms of the cert path. I'll simply throw out just two other ideas on methods. One is, in all of this, there's no substitute for the timeless concurrent engineering of having early involvement by all downstream disciplines, having the quality professionals, the manufacturing professionals, engineering professionals all at the table at the beginning of a new design where we know we're going to insert additive. One of the great other lessons from the automotive industry is great methodology, QFD, that has existed for probably 30 or 40 years. You may or may not be familiar with it, but it's a matrix-based approach of taking customer needs down to a product. And one of the things I think in our industry, especially in defense, why perhaps QFD didn't take off a lot is that we would begin with system specs from our customers and requirements elicited with shalls, and we would simply begin and didn't have to do the heavy lifting of the QFD mapping. Well, if you do QFD right, you can begin with customer needs, get the tech parameters that are your TPMs for your product, but you can take it to another house of quality, which is the process design that's going to make the product design real. I think it's going to be a very interesting thing to see for some of us, to see if there's a small renaissance of matrix-based or QFD methods where you take the case in Detroit. If you're automating a paint process, a drip is a very bad day. And so QFD helped deal with the design of aperture of nozzles, flow rate of materials. Many of these kind of things are have their analog in additive or other techniques. So that's some opening thoughts.
Well, from our perspective, first and foremost, when we talk about additive and how are we going to get to cert in rocket engine products, if you will, material characterization is first and foremost. And so most of what we've spent our time on in the last 5 years is characterizing the materials that we're going to use in the additive process. It's only lately that we have achieved the kind of process consistency with the characteristics we want in the metal that allowed us to build parts and start putting them into hot fire scenarios. So first and foremost, it's the properties, and we've spent the time and the money to get those properties down to where they're consistent and very little variation in order to be able to reproduce the part. Once we've done that, ultimately, in our products, the hot fire test is the ultimate certification, and there we want to be able to show that the overall design of all the parts working together, okay, can operate with as little variation as possible. So there's a lot of statistical process control techniques that we want to use at the system level, not just at the piece part manufacturing level. So I think the rapid development of the material characteristics and rapid prototyping helps us do that, because we can do the cutting and the stretching and all the techniques. But then getting those parts into hot fires so that we can see that we have minimized the variation, which tends then to allow us to cut down the amount of effort it takes to run a CERT program. And that's kind of the direction we're headed from a rocket engine perspective.
So I'm really glad you asked this question. So we're the company who's certifying this part in 2015. I've spent a lot of time in the last year talking to the certifying agencies about this very question, both civil and government agencies. And obviously you all have answered this very well. There's no shortcuts. I mean, that's the short answer, and I'll give you a longer answer as well. And so I think what we normally start this conversation with is all of our companies have the processes already in place. And I think because this technology is new to us, we start to think we need to invent something new with regard to how do we certify and qualify, and you're right with regard to material. If we had another new casting alloy or a new forged, we would just follow our normal processes and procedures to qualify it. And so that's been our approach since day one. And so we've followed those same procedures and methodologies, and it's not, it's a lot of work, and it's a lot of process. So I can walk you through a little bit of what that looked like as we walk through that certification process. I'll start with an anecdote. I was at a meeting talking about this topic with one of the certifying agencies. And one of the concerns is not just for the OEMs, but for third parties. There's a concern that, and I think one of the concerns is it has the barrier to entry, it's perceived that the barrier of entry has lowered, that other people can start replicating some of these components. And so I had brought a part, and I pulled this part out of my pocket, and I said, a week ago, this is an out of production part, and there is, and the only data that exists is a PDF file. And a week ago, that's all that existed. And from a PDF file, I now hold the part in my hand. So it's the equivalent nominal geometry, equivalent chemically, and here it sits in front of you. And so I think that's really where we all maybe get a little concerned. And what I'll tell you is that even though it's got those same characteristics, it's not the equivalent part as the certified part. And here's why. When we certify, for instance, the LEAP fuel nozzle, we certify it on a machine, and that machine has been demonstrated to have the same material characteristics that you've shown. That machine has shown statistically to equal the same material properties that we've designed the part to. That machine and every other machine has shown, so we have to show that statistically, not just one piece, but on a statistically significant basis. It also has to show that geometrically, every single part that comes out meets the specification of that fuel nozzle on a statistically significant basis. So metallurgically and dimensionally, it's got to meet all of those qualifications, and it's got to do it on a statistically significant basis. And so just as a data point, for us to be able to do that for a single machine takes us about 6 months. So for one machine, for us to qualify, is a 6-month qualification. So we call this vendor substantiation or source substantiation. I don't know, different companies have different names for that. It's no different than if I qualified a new casting mold, right? So that's the analogy we've said, is our machine is a casting mold, and I just need to qualify my new casting mold, and I got to show that the material that comes out of it's equivalent to the material that I've designed to, and it meets all my standards, so that when these parts come out, I know that all of the analysis I've done in my little design lean lab that I had going on, it meets that standard, and that dimensionally, it meets all of the requirements, so that I'm confident. So that's very different than the part that I pulled off a PDF file and I printed one. Yeah, nominally it's got the right chemistry, and nominally it looks kind of like the part, but statistically, there's nothing I can say about it. And so that's the conversation we've had over and over again with the regulators and internally. I mean, we're our own toughest critics here. I mean, we don't want a black eye not only for GE, but for the industry. I mean, as soon as there's an additive part, we don't ever want an additive part having that press release, right? That's for all of us. I mean, I don't want it for me or for you or for any of us, because, the press would immediately link that to, 3D printed part, bad things happen, right? That's the last thing any of us want to occur. So we've been our own worst critic in this area.
I think he hit it right on. I mean, that is the issue with that. I mean, it aligns with, following the example I gave with the structural certification, going from 5,000 tests in the 80s to over 100,000, in the 2000s. I mean, following the same processes, but it is there's no shortcuts, and you're going to have to do it. And this is one of the things that you have to be aware of, and there's a number of others, but that you have to be aware of, to really realize the benefits that this technology or any advanced technology really has to offer.
I'd like to now throw in there's a big effort in standardization going on. There's a committee within ASTM called F42 to come up with standards in additive manufacturing. It's about 4 or 5 years old now. Certification is a topic that is discussed a lot. The whole community is very interested, all the users from aerospace, et cetera, et cetera. I don't know that there are any standards yet on certification. So yes, it's a lot of work. People are taking kind of the standard approach to certification and applying it in additive. That seems to make sense. It requires a lot of data, it requires a lot of work. There are no shortcuts. I would invite anyone who's interested. We have an upcoming ASTM meeting, F42 meeting at the end of the month. Let me know if you want more information about that to get involved. So that process is ongoing, but it's rather slow. It's very difficult. Now, how can design affect all that? Let me just say very briefly that we don't really know yet. That's going to be a conversation we have ongoing, probably in a few years from now.
Any double E's in the room? Any electrical engineers by training? All right, hooray. And then I was going to ask, anybody over 30 years in the industry that also with that background? I'm a double E by training, and actually started doing CPU design in my first assignments within industry. And this reminds me, the evolution of additive reminds me a lot of where the semiconductor industry was in about the 1970s. Because as we started to proliferate integrated circuits and fabricate integrated circuits, when there was silicon in Silicon Valley. It was a very bad day if you got a design into the laboratory and you didn't know whether it was the process or the design that was the root cause of failure. And I think we're all on a journey together here. One of the great lessons learned that can be captured out of the semiconductor industry is if you follow that at all, and there are new generation of ASIC feature size shrinks that come out from Intel's and the other fab houses around the world, there is a lot of work done to rock solid characterize each new node that's released so that you have confidence that when you get into the lab, it's going to be a design error as opposed to a process problem. And so we have this journey now where we have, we're starting to formalize our characterization process for additive, much like the semiconductor industry did 30, 40 years ago. Hopefully we look back in 10 or 15 years and say that we have a systematic, widely shared characterization data that all of our designers can trust for titanium, for polymers and the like, and really the design is all that's in play. That's just a kind of an adjacent industry thought.
All right, so I'm going to ask one more question, and then we'll open up the floor for questions. So prepare your questions now. So one last question. We often hear that, especially with additive manufacturing, that complexity is free, and I think both Steve and Mark talked about this. But there's also sort of a desire for elegance in a design or a simplicity in design. How can we ensure that even with all this flexibility to design really complex structures that we end up with nice, elegant design in the end? Anyone?
Well, you know, the comment that was made earlier in terms of simplicity, right? I mean, so you know, you want to make something. I mean, I forget who had the quote, but you want to make it as simple as possible, but no simpler. Right? So, and that's elegance, right? I mean, that's an elegant solution. So, but the complexity offers you performance increases at really, and complexity is free is really the marginal cost, right? I mean, you know, there's a cost with implementing things like additive, but the marginal cost of adding complexity is negligible. So once you start with a basic cost, then the marginal is, so you can get significantly enhanced performance by adding complexity, but no more than is necessary. I mean, keeping the solution elegant. But again, this comes back down to, in my view, the design of the part and the process to arrive at that solution. So I think that's something to keep in mind talking about this.
Some of the things that we've been doing, when you integrate functionality and you keep additive in mind, and it allows you to combine parts and functions together into a single part or system. Although it may look complex, in reality it is elegant from the fact that everything is one piece. Cost goes down, test becomes easier. It may look complicated, but it's actually simpler and much more elegant when you use an integrated approach with additive. And it allows you to do things that we've never done before. Fluid passages are critical for us, and subtractive techniques make fluid passages very difficult to verify, etc. With additive, it's a breeze now. So to me, just because it looks complex does not mean that it is, okay? The solution is elegant if it does what it's supposed to do, and you can do it with the minimum number of parts.
Yeah, I was going to make a very similar comment. A wise man once said, "Simple is as simple does." You might have heard that. Yeah, so I think when we think of, traditionally when we think of elegant, we might think of a straight pipe or a very simple geometric. And I think in the additive world, elegance may be the inside of that bird bone structure or that tree-like structure. So I think we're even redefining terms in this new space, right? And I think, you really need to, it's really more of a physics design or more of an organic design. So in my new role as the additive leader, one of the things we're doing is looking across our current portfolio of products, both in develop and existing, and looking for cost opportunities. So that's been kind of fun, taking the additive hammer, if you will, and seeing what nails we can bang out with it. And one of the phrases that I use as we're trying to help engineers who really don't know a lot about additive is I say, additive loves complexity, which is kind of the opposite of your question. But what I mean by that when I say additive loves complexity is that cost in additive is really more directly related to volume or weight. Volume. So in other words, I can print a 1 pound cube or a 1 pound spider web, and in essence, those will cost me the same on a printer. So in the more elegant design then is the spider web than the cube. So when I look into these engine structures, and as I'm combining parts together, the actual geometry can actually become very, very complex. But then that is, in my mind, more elegant because I'm combining pieces together, combining functions. I'm doing multiple things, but I'm doing it now with one part and probably in a more weight-efficient way, and certainly a more cost-efficient way.
Maybe elegance is related to more efficiency, if you will.
Yeah.
So I think that there's a lot of interesting things that could be explored there. When you give additive manufacturing to industrial designers and artists, you can get some really, really amazing results. So people have designed chairs and furniture and housewares and lampshades and all that kind of stuff to be made in additive, and you can get just beautiful results if done right. If you have a little bit of spare time, Google additive or 3D printing fashion. Now we're going off into a different area, but dresses and hats and stuff you cannot imagine. We'll come back. But it's really great to just look at the photographs and just see, again, creativity. What people have thought of. None of that's necessarily directly relevant to aerospace necessarily, but it's what people interact with. Again, some of these designs are very elegant. Some of them are the opposite of elegance. But again, very interesting sort of thing.
We've had a lot of great discussion about design for simplicity, let's say at the mechanical component or structures level. And Mark, I love that example you used of your lead engineer coming in saying, hey, we're thinking about this all wrong in terms of the paradigm change. There's another aspect that I think is very ripe for both academia and industry, and it's design for simplicity at the platform level. Aircraft, spacecraft, et cetera. Yeah. We have had this exponential growth of let's call it the static complexity, which would be the bill of materials, the number of millions of logic gates, the source lines of code, all of which introduce the risk of unintended behavior in a system. I'll tell a very short story just to stretch everybody's mind a little bit. We're coming up on the 50th anniversary of the Gemini missions, which were the precursor to Apollo and the moon landings. Our company designed the mission processor, or the flight computer, for the Gemini spacecraft. To give you a sense, 50 years ago, for a spacecraft that 14-day duration in Earth orbit, obviously the ability to achieve orbit, rendezvous, dock, successfully land, extravehicular activities, etc. Let me give you a few specs on the Gemini flight computer. First of all, because of the technology we had to work with, 57 pounds, 95 watts of power consumption, only 31 fixed point instructions was the instruction set. Anybody want to take a guess of the onboard memory? 4K. It was 4K of hand-wound core memories, and the total lines of code in the Gemini flight computer for the entire mission, which, by the way, there had to be reloads while you were in flight for the like 20 case lock flew all of Gemini. And so sometimes I think we all in the big, as we've been caught up in, it's almost the salad bar theory, the larger plate we can develop, the larger we can fill it. The ability to step back at system level designs, really think what the operational need is, and do we need to push the curve on complexity, and then that scales all the way down to the mechanical and the subcomponents. So that's just an interesting factoid 50 years later from manned space.
All right, do we have any questions from the floor? Yes.
Sure. Yeah. Head first.
Personally, yes. I don't think we're quite ready yet to sit down with the customer and say, this is the way the process needs to be done in the future. We'd like to work with you to get it updated so that we can all do this. We're not there yet, but we will be someday, and yes, we will need a revision, in my opinion.
I don't know enough to answer, so I'm going to abstain.
I'll offer that an echo to the yes.
Yeah.
And from a standpoint, actually, if we think back several secretaries of defense ago, we go back to, I believe, Secretary Gates, who may have introduced the concept of the 80% solution. And one of the things that I think in the very front end system engineering process that could be a very constructive journey that the DoD and we could take together is more of a working space between the operational need and what the design needs to be. Because if you can simplify requirements greatly, there's this great quality lever, right? Where every issue that might pop out in production that, let's say it's $1,000, if you can find it in detailed design, maybe it's 100. You can find it in concept design, it's about 10. If you can solve it at the requirements level, it's probably $1. And so any modification to that allowed or perhaps institutionalized a structured two-way dialogue on the ConOps as opposed to a system spec being issued to each of us with a statement of work, with the SE being done uniquely within the DoD, I think there'd be a great benefit for us iterating. And maybe.
Yeah, no, I agree with that. I mean, I'd say yes, that is going to be required. I don't think we're quite there yet, but I think absolutely.
Yes.
I guess I'll jump in first. The maker movement has really revolutionized a lot of what a lot of young people do and how they do it. And so a lot of universities are creating maker spaces where the students can they're spaces, right? They go there, they come together, they design new stuff, they have a lot of fun, they make stuff. Some of it's done with additives, some of it, however you want to do it. The point is to get more kind of hands-on activity, right? Let's go back to Mark's comment. The lead engineer, had to be intimately familiar with the manufacturing process, right? We need our graduates to understand materials and fabrication and design and the engineering and how they work together. And the best way to do that, I think, is to give them a whole bunch of opportunities to do this, right? To design things and try to make them work. Fail early, fail often, fail repeatedly, and so they'll eventually really get it, and they'll get the interactions, they'll get the system level perspective. So it starts with some new curriculum changes, some potentially new courses, but also the willingness to have maker spaces at universities and give the students the freedom and the opportunity to take advantage of them as best they can.
I've gone around our company and talked to some new hire engineers. I mean, and they sort of expect that you're going to have, in the CAD room, a 3D printer. I mean, because in some schools, I mean, they've actually been using these and working with them. So the young people, as they come in, their expectation is that they're going to be doing it. And in those areas where they don't see it, they start wondering, where did they go? But I think, in my company, I mean, we are attempting to put, in every CAD room, one of these things. And I think that is, and then provide training as well, so that you just don't have the equipment there, but how do you use it? How do you get the most out of it? What are the design principles that can be used so that you can start thinking about how you design for the process?
One of the additional things we've done is, now that we've begun to apply this mixed model management I talked about and the microsystem thinking and the shift in the way you design, we have taken that now to the local universities in the Cal State system, and we've begun a partnership with them to pass that information on. Many of the professors have gotten extremely interested in the approach, and we're hoping to affect the curriculum, at least starting with Cal State schools that we normally draw from in terms of hiring. We'd like to expand that beyond that, but we're still at this first stage, and if we're successful with Cal State, we'll probably move on to some of the other major schools that we normally deal with.
Yes.
I'll start with a simple one. Each year we hold a series of corporate-wide workshops or conferences that brings our professions together, whether it is the EE, ME, software systems, test communities. And one of the things that we've done the last 2 years, and we're going to continue to do, is we have a special thread in each of, one is advanced manufacturing technologies to give exposure to those that attend, and also to have them start thinking about how this is an additional part of your toolkit. Another is a second parallel initiative that a peer director of mine works on, which is advancing complex systems and how to deal with complex systems thinking. So we are taking an outreach at the workshop level and also on our intranet or our storefront for corporate engineering to give some exposure. That's just a couple ways. There may be similar.
Yeah, we do similar things, and again, like I said, in particular for additive, I mean, one of the things that we put together courses, and we started with the design engineers. I mean, that's we have these series of modules, and so the design module is the first one to get out there. But in terms of targeting specifically, cognizant engineers, we leave that up to the business units and the programs to define who they want to send to those. But yeah, that's a good comment.
We have begun to codify the approach that I talked about in the way we look at design now, which is different from our command media of the past. So we have actually gotten to the point where engineering has been willing to rewrite their procedures, if you will, in the command media for how we do this kind of design approach with the mixed model management. We just began that about 6 months ago, so we're early in getting it all down on paper, if you will. But our goal ultimately is to change the engineering procedures such that everyone has to go this route, if you will, when we do design. So we are trying to codify it from that perspective. As far as the technology is concerned, that is really mostly the workshop kind of approach we've used as well. Try to bring in groups of people to see what goes on, see the machines in operation, and understand what comes out. What do you have to do to finish the part after it comes out? Because that's, you know, just running it through the machine is not the last step in the process. So we've tried to do that with groups.
I would say likewise, we're doing all these similar things at GE. The one point I would like to make, you made a statement earlier that I think is very important around the value stream. So just as an example, the fuel nozzle alone will be manufactured at quantities of 40,000 a year. That is no small undertaking when you're talking about an industry that's largely a prototyping industry. So just to be able to stand up a plant, ours will be in Auburn, Alabama, to stand up a plant just to make one component, and now you're talking about growing that across a business. So I agree, you start with the engineers. That's where I come from. I'm in the design community, and I do believe that's where the heartbeat of the company is. If we're talking about growing this even into the architecture of the engines, into systems and subsystems, there's a value stream discussion that has to, what are those machines, what are those materials, right? I can sell all day long, but the first question I hear at every single meeting is, what materials are available? How big is the machine? Right? So there's layers of conversation here that need to be addressed.
Layers of value streams.
And value, right.
Integration of value
That's right.
streams.
So the training is one, but this is a multifaceted discussion.
Yes.
Take that first. Sure. Well, the short, honest answer is I really don't know. All right, but another way to look at that is when we look at the schools in the College of Engineering at Georgia Tech, for example, mechanical engineering and aerospace engineering, to some extent civil engineering, to less extent electrical engineering. We collaborate a lot, work together a lot. There are individuals that collaborate all over the place, but from a school perspective, there's a lot of collaboration between ME and AE, for example. There's little between ISYE, our Industrial and Systems Engineering School, and a lot of the other schools. All right. So when you look at aerospace manufacturing or advanced manufacturing in general, there are people in our school that are focused in manufacturing a little bit, but it's really logistics and supply chain. At least within our school there's not a lot of manufacturing process kind of people, nor are there a lot of people that, frankly, are collaborating with others that are getting into that. How well does that translate across the country? I really don't know.
I, for one, would not give a harsh grade to higher education from a standpoint that there's a unique point in a student's life where they have a chance to really master the first principles of engineering, and that is undergraduate school and possibly a master's degree journey. And I know, perhaps I'm interested in the perspectives of others, much rather hire a very strong electrical, mechanical, industrial engineer, aerospace engineer who's firmly grounded in the principles of engineering and design, and that when they first encounter a design that breaks on a vibration table, or it fails at 35 below zero for reasons that we don't understand, has a background to begin to attack that problem, and that we can then mentor them on emerging technologies that may be new. There's certainly enrichment opportunities that you all have in capstone courses or in the one-credit guest lecture opportunities to bring folks like us in to come and talk. But boy, I would never sacrifice first principle engineering for emerging. I appreciate other thoughts.
Yeah, no, I agree with that. Yeah, absolutely. Yeah, I'll start off by saying, we've been thinking a lot about that lately, and I think that it really, from what I've seen, it really depends on the specific applications that we're talking about, the quantity of parts that you're talking about. One of the concerns I have is that, we have such a broad product range that and the technology is moving so fast. If you capitalize that you're going to build it yourself and you're going to go buy the machines or whatever, in 2 years, is there something better out there that can do it faster or cheaper and that kind of thing? So how do you balance that with spending a lot of money to capitalize the facility to do it yourself, or do you just partner with some key suppliers and let the new machines be brought in and into the supply base? One of the things that we did when we were doing the polymer development for the ECS ducting is really, we don't build those things. We worked with the supply chain and we built up some key suppliers that we could go to do that. I think that is one model, but that's for that specific application. As we look at other applications, it may be a different solution. So I think it's in our case, because of the broad range of products, you got to take it on a case-by-case basis.
Well, from our perspective, we've already looked at just existing product line and looking at the number of parts that we'd love to see come out of additive machines, and there just aren't enough machines at the size we need for the parts we'd like to have that exist today. Certainly we don't have them, and the capital cost of getting that many machines to do what we want to do would just be prohibitive in the overall affordability equation. So we would look to encourage the supply base to continue to capitalize for us and work with us. And then the other point Andy made about the technology changing, absolutely, we get started and we find that the technology either changes or we find a brand new technology. We don't want to be so overcommitted to one that we can't rapidly make the adjustment to whatever comes next. So we have continued so far down the path from an additive perspective of cultivating the supply base.
I think it's an insightful question. And I think your answer on case by case is the right answer.
Yeah, if you've got 40,000 parts you're making, that's one answer,
Yeah.
versus if you're making
Right.
50 a year type.
Right, so GE's probably done both, right? So we've acquired Morse Technology, probably the largest, at least US-based prototype manufacturer. Avio was a company GE acquired which had an additive manufacturing arm of it. They've actually vertically integrated a powder manufacturing. So they do some material, right? And then, so I would just say keep your eyes open. I think anything is possible. Not everything is the right thing. This whole area is very exciting and very interesting to watch. I think you'll see everything from full vertical integration all the way down to the materials to there'd be places where it doesn't make sense, right?
To maybe just give some numbers to your question, that if you look at any of us that are large platform system integrators, we probably outsource, or I'm going to use a range, 40 to 70% of our decisions are buy versus make. And actually all of us, by definition, have make-buy process decisions that we're doing all the time that do weigh that cost of capital with what makes sense against the core competency of what we do very well.
That's right, critical IP. There's so many factors in that decision, yeah.
So it's not lost among us. That's definitely for sure.
I think it's a very insightful question.
Yeah, we think about
Great
it all
question.
the time.
I think it's also a life cycle, a technology life cycle issue, right? We're fairly early in the commercialization of additive. In the case of the fuel nozzles, I mean, there's no existing facility that GE could have turned to fabricate 40,000 of these things per year in metal. So, and you know, composites at Boeing and the other aerospace companies, again, early years, they did it in-house, then they farmed it out. You know, another data point here is that there was a time when Kodak turned their own screws to assemble their cameras. Kodak doesn't do that anymore. I'm not sure what Kodak does anymore, but so yeah, you got to be smart about these make-buy decisions. Invest strategically.
Yes.
Well, I'm probably at one extreme.
Right.
You know, the interesting thing about the fuel nozzle was, I think conventional thinking would have told, had we sat down and thought about it, we probably wouldn't have done the fuel nozzle. Maybe we did, that's probably an overstatement. But conventional thinking says, let's create a multi-generational program plan, right? Which says you do something simpler, maybe something that's not right in front of this ball of fire, right? Maybe something that's not as critical. Maybe not something that's on the largest production volume engine ever. But the implications of that were that it took what would have been a traditional technology curve, and it just put it vertical. Right? It just took a team and required us to meet a timeline. No one says that you can schedule innovation. This is about as close to scheduling innovation as it could be. It required us to meet a timeline and on GE's most critical product platform. And so, and not only did it require us to meet, you know, I told you about reliability, I told you about all those things, but on a cost point. And that cost point wasn't just simply creating a geometry, it was creating a value stream. Because a lot of this requires us to think through that entire process. And because this was the first of kind, if you will, what it did is it allows us to leverage that back into, now likely the next one probably isn't going to be 40,000, hopefully. But it allows us to leverage that learning across a much larger, you know, many more parts. So I don't know if I'm answering your question, but volume in that case forced us to think in ways that think about additive in ways that I don't think anyone else was thinking, frankly. And now when I look at parts, I guess I don't think so much about volume because it's kind of like I've already thought about it. It's like I've already sort of mapped out what high volume looks like. So let's say it's 1,000 a year. It's like, well, I'm going to just put that in the LEAP fuel nozzle production factory. And so I want to take all the benefits that I see in that factory, and I'm going to use that cost. Because why wouldn't I? So at least I don't think I would think about it any differently.
From our perspective, in the liquid propulsion side of the business, where we've done most of our work, liquid propulsion is a relatively low volume activity. So volume doesn't really drive us too much in terms of the decisions that we've made in applying additive to the liquid side of the business. What we're just now getting into is applying additive to the solid rocket side of the business, which is higher volume given the tactical missiles that we support. So we're just beginning to look at what do we have to do for additive in that side of the house, which does have much higher production volume, and we're not there yet.
You know, another aspect of this in terms of, we've got some relatively low volume activities, but traditional methods require extremely long lead times. And so, again, that just exemplifies that, it's really a case-by-case basis when you look at the business case for each of these potential applications. Where does it make sense to include this in the trade for what you're going to potentially use as the manufacturing process? So, and then again, there's lots of opportunity in aftermarket where the volumes are unpredictable, and traditionally there's lots of inventory kept and that kind of thing. So this is an opportunity for reducing those just-in-time type supply.
So Sid's a thought leader on our advanced manufacturing team, and so I appreciated you guys' answers. And I think one of the things about our industry is many of us would characterize our businesses as being low volume, high part number for an awful lot of the products we develop. And the GE example is probably one of the great case studies right now of where you all thought, go big or go home in terms of the commitment to the, and so must have been a set of really, let's say, courageous management decisions, Mark, in terms of those investments. And could you share, was there some gating that happened in that, that 3-year period or 4-year period to where you were making the decisions on investing in the plants that was, key milestones where you had to show that the design was maturing to do the big bet?
Yeah, I will tell you, it's one of the rare times at GE, a large corporation, where it was really not a corporate approach, if I could say that out loud. Michael Benjamin's sitting here. He can maybe shake his head. He's part of the fuel nozzle team. He's staying quiet. He's probably going to leave now that I pointed him out. We created this team that was, the best way to describe it was a startup company mentality within the larger corporation. And Mohammed Edashami, who's the vice president, is a very unique individual. He is a risk taker in a way that probably no other leader I've ever worked for is a risk taker in that way. But risk is sort of in quotes, because the risks he takes always are successful. So from day one, we started this team, and as I described, I started hiring people. The first 6 months, I was as much an HR manager as an engineering manager. I was just hiring. We would have team meetings, and the first thing he told me, he came back from our oil and gas business, and the first thing he told me, Mark, he said, first thing I tell you about engineers is engineers don't like to execute. They can, I want this to feel like an operations environment. I want this to feel like supply chain. Right? He was all pumped up about supply chain. I'm like, okay, and I said, so in order for that to happen, I want to come to your meetings. So probably for 2 months, 3 months, I don't know, yeah, it's a long time. He came to every one of my meetings. So I had a vice president sitting in my meeting. So I guess that's, if we're a small company, I guess I had, sort of the board of directors, which was him, and then our general manager, and then all, since he came, it was every person all the way down to me in these meetings. And it was a very operational environment. We had the visual management boards, and we were tracking stuff, and it was very much higher energy. But because of that, there was this conversation about, do we have gates? Do we have, should we have a backup? Should we have the traditional subtractive design? And, at what point are we a go? We did have one person sort of working on a backup design, but there was a point where this was it. We were just go. And it was interesting, at the end of all of this, I did create a video. I pulled the core people in and I said, how did this happen? And I just kind of sat back and went around the table. And the kind of feedback I got was, it was actually this operational, so these are design engineers, by the way, they're talking, right? So these are not normally people who say these kind of things. They said it was that very operational mentality driven by a vice president that we called it say-do mentality, like I'm gonna commit to it and I'm gonna have to deliver, which drove it. It was that high energy, like somebody said, it was that foxhole mentality. You walked in and your pulse rate increased every day. It was that kind of high energy. So it wasn't, I don't know, Michael, you can correct me. It wasn't a traditional gating process. It was more like skunk works. It was more like a wartime mentality. Like, I made a commitment, we made a commitment, we're gonna do it. I mean, it was like, innovation will occur here. And then once we were committed, and then once we bought Morse, we were in. So then we said, okay, we're gonna have to build a plant in Auburn, and we're gonna industrialize. And so here's the cost number, X. Okay, how's that gonna happen? I don't know, we're building a plant, right? I mean, it was kind of that small company mentality, and we'll figure, this is how we're gonna do it, we know. And so it was very much a different, and I've worked for GE for a long time, and I can tell you that's not the way we traditionally have done things in the company. But if you were in the talk earlier, I heard someone else talking about that small company approach. And it really fits well with this additive mentality. We were doing things fast. We were running off that test build. I mean, it was just fast. We were able to execute.
Are there other questions? Yes.
Well, I would say there's a combination of, maybe a combination of push and pull that occurs within each of the companies where if we have a business unit that has a yield issue or an outsourcing supplier problem or the like, to where we can bring an internal solution with advanced manufacturing to bear, we're very responsive to try and respond to that, partner with that business unit from corporate and take the task. And then there's a list, I think, of more reflective, let's call it should-dos, in terms of now that we know what the possibilities that would exist within additive manufacturing as example, or next generation electronics as another one of ours, what are the should-do initiatives we should launch because they just make strategic sense. And so that's a short answer. I think it's a combination of a push and pull process. Welcome other thoughts.
Yeah, no, I think that's true. I mean, it's, you know, we respond to internal requests for help. I mean, typically, you know, aerospace systems, you know, you love it when you can get, you know, the weight down. There's always a weight issue, and then you just, is for a particular technology, does the business case make sense? And if it does, then you know, we can go forward. And I mean, you know, we're working on stuff right now for weight is a real big issue, and being able to consolidate number of pieces into one at a reduced weight. And you know, sometimes the lead time is long for a piece. You're going to wait for, you know, a big piece of metal that you're going to machine out, or can you just additively grow it? And then if you can combine parts and get the cost down and the weight down, you know, then it makes sense. But then again, you know, in some of these cases, where these are structural parts, you got to think about, okay, what's the structural certification cost? It's got to go with that, and then, you know, if it's a one-off type thing, that's great. But you know, if there's a certain production rate, you know, is the supply chain going to be able to provide this? You know, working with suppliers. I mean, like we talked about, the technology is changing. Well, you've got this one thing, you've qualified that. Well, the supplier's now going to upgrade and buy a new machine. Well, now you got to go and requalify this, because the new machine is not going to necessarily make it the same way. So all this stuff comes together, and you know, the various businesses and programs in our company, you know, are, you know, well, once you help them get over the hype, you know, then you can start looking at it rationally. I mean, people call me up all the time that, you know, they've heard about this, and you know, that you can do this wonderful stuff, and you know, complexity is free, and you know, all this stuff, and so they're just thinking cost savings and not thinking about the associated costs that get to the benefit. But I think, you know, the SMEs that we have within the company in these areas work with the different businesses to identify potential part families, and then does the business case close. I think that really is the case. And when you have a large product line, I mean, there's lots of opportunities potentially, and some make sense and some won't on closer scrutiny.
Well, from our perspective, additive became an immediate part of a long-term affordability strategy that we had put together. It was just one of many planks in that platform. As we've gone forward, however, it's become very clear, for the reasons Andy talked about, the application is a case-by-case basis and based on a business case. So that's pretty simple for us.
Yeah, you talked about complexity. That's where, you know, when I say additive loves complexity, it's normally when in those reviews is when we're looking for things. That's where I say additive. So very simple parts typically are not going to be wins for additive. So what I normally do when I'm talking to teams, and we're doing what amounts normally to a cross-section review, we have a cross-section of an engine and we're looking for opportunities, been involved with quite a few of these, is I normally ask them what their problems are. Because for us, it could be cost, or it could be fuel burn, or it could be reliability, durability, and what, you know, additive can really help us meet all of those requirements. And one of the things I asked people, I said, so you have a life problem, you have a durability problem, do you ever consider additive? I mean, that's not always our first thought, but additive can be a solution in those as well. So I normally ask them, what are your problems? Where do you need help? And then we can start the conversation there. Now, cost is often top of our list, and so I've had reviews with cost teams, and all we do is look for cost. I've had fuel burn initiatives, all we do is look for fuel burn. I've also had lists of just engine program. Here's a list of all our problems, and there's scattering of reasons why. Or you have development. So here's a brand new engine in development, and then it's sort of up for grabs, and now we're just looking for, show me this part. So somebody say, can you print this part? And I'll say, can you show me the context? Okay? Can we put these together? Why are these two pieces separate? And you just, then it's the system conversation. How much of this can be combined? Is there an assembly or maintenance reason? So it's a lot of time, it is a conversation. There's multiple facets, in my experience, multiple facets. And the earlier you get in that design discussion, the bigger it can be, right? If it's fixing a problem, then you're probably talking about one part, or maybe two. If you're early in design, you can really take on 20 pieces.
You know, Art mentioned business value. As we look at projects, there's at least 5 areas, and I think it would be probably unanimous across the table here, but number 1 is a solution or technology, is it relevant to a customer's problem that we need to solve? Does it help affordability and cost? Does it help with flawless execution? Can we drive quality up as a result of it? In some cases, can it help us break into an adjacent market? Or in some cases, as U.S. companies, can it help us with international growth? Those are 5 areas that we think about when we think of business value and try and categorize projects against
Yeah,
them.
you bring up the business side. So sometimes strategic reasons why we would do it.
Yep.
Yeah.
All right, I think we're now out of time. And I really want to thank you all for providing such valuable insights into advanced manufacturing. And I think this has given us a lot to think about. So, and I want to thank you personally for taking the time to come and be on this panel, and I very much appreciate it. So let's thank our panelists.